All right, let's get started today. So we're going to talk about stoichiometry, solutions, and solubility. So let's read it out. We'll do some basic stoichiometry first. So last week we learned how to use the periodic table of the elements. Today we're going to learn about how to do stoichiometry, balance chemical reaction equations. Then we're going to move on to solutions, how to create them, dilute them, and then we'll talk about solubility. Okay. So when we start, we're going to take a look at the concept of the difference between mass versus moles. So let's define what a mole is. So 1 mole of something is 6.02 times 10 to the 23rd things. It's just a number. Like a million, a billion, a trillion, a zillion, whatever, right? A mole is just a number. It's 6.02 times 10 to the 23rd things. The reason that it has meaning is because 1 mole of carbon atoms is equal to 12 grams. So since an atom itself is so small, we're looking at things on the submicroscopic level. You're going to need like a mole's worth, this many number of atoms, 6.022 times 10 to the 23rd atoms in order to make 12 grams. And everything on your periodic table that you guys are using as atomic mass units is some gram per mole ratio for that number of atoms. So every element that we looked at on the periodic table of the elements has a clear gram per mole ratio. And we call that its molecular weight. Oxygen is 15.99 or 16. That 15.99 is also taking into account the weighted mass of all of its isotopes. Typically, I try not to let students record. I don't think you have permissions to. There was a question if we can record lectures. Yeah. But you're more than welcome to copy notes. And if you need notes, I have all my notes on PDF as well. So if you just email me, I can just send them to you as well. So you can get the notes on PDF if you need it. If you miss class, obviously, I'll send it out. But yeah, if you feel like I skipped over something and went something too fast and you want to look over my lecture notes again, every student's able to email me and I can send them my PDFs of my lecture notes, okay? We're just doing basics and reviewing, so it's not like groundbreaking Nobel Prize peace stuff, right? Or Nobel work. So definitely, yes. So feel free to just email me and let me know. Sorry, there was a question that came in if like you can record. I generally don't like let students record. I want them to be able to take active notes, be active, awake, alert, and learning. I find that when you get a PDF, you kind of just, you know, you're like, yeah, it's right there. I don't really have to write anything. I just listen. And then a lot of it goes in one ear and out the other ear. Okay. But if you find that you learn better that way, then by all means, feel free to ask me for my lecture notes afterwards. Okay. The next thing that we need to know is your molar volume of a gas. Molar volume of an ideal gas is 22.4 liters per mole. And this is at standard temp and pressure, STP. By the way, STP is 0 degrees Celsius and 1 atmosphere for pressure. So this is the pressure, this is the temperature, okay? And this is the IUPAC definition for standard temp and pressure. For the EPA, which is a different definition of standard temp and pressure, it's 25 degrees Celsius and 1 atmosphere. Yeah. What's the word before gas? Ideal gas? Molar volume of an ideal gas. Yeah. So depending on who writes your passages for your tests on the MCAT, I've had students come back and tell me it's either an EPA question or an IUPAC question. If they don't tell you that it's EPA, you assume IUPAC, and it's 0 degrees Celsius and 1 atmosphere for pressure. But if they actually have an EPA and it's like EPA cited, when they say STP in the passage, it's 25 degrees Celsius and 1 ATM. Okay, so just keep that in mind. I've had students come back for multiple tests and tell me that was the case. So I don't want you guys missing any questions based on STP and what the understanding of STP is. Environmental Protection Agency. EPA's Environmental Protection Agency. They're the ones that set all the guidelines for, carbon emissions and stuff in the United States. No.
Will they tell you which one it is in the passage?
Oh. Sorry, was there like a statement or question?
I'm asking, in a passage, will they tell you if it's IUPAC or EPA, STP?
Yes. It'll state that it's EPA, or it'll cite it that this is an EPA article in the passage. So they always have citations of where they pull the passages from.
Gotcha.
Yeah, so they'll cite it there, and then when they mention STP, they mean 25 degrees Celsius. But otherwise, if it's not cited as an EPA passage, then you can just keep it as like IUPAC standard. Okay. Sorry, I was like asked. I thought you asked me to like cite it, and I was like, I believe it's from an AMC test, so I can't really get access to those. That's what I thought you meant, Mo. Okay, so let's take a look. So all of that knowledge, right? Understanding your atomic mass units and your gram per mole, and needing that, a mole's worth of atoms to form that many grams, allows you to do these types of questions, right? These basic stoichiometry type questions where you're finding like limiting reagents and stuff like that. So first question for chemistry. So if we have 5 grams of hydrogen gas and 64 grams of oxygen gas, how much water, vapor, gas can we make? So I'll let you guys chew on that, and then we'll go over how to approach these like limiting reagent type problems when it comes to stoichiometry. See if you guys remember how to write a chemical equation, chemical reaction equation, balance it. You have the periodic table from your workbooks. You can look up the actual atomic mass for each, find the limiting reagents, and then solve for what we're asking for. In this case, how much oxygens, how many grams of oxygen gas, of water do we have? So how much grams of H2O can we make? Okay. Jonathan says 36 grams of water. Anyone got another answer? I'm going to list the four most popular answers, and those will be your answer choices for your MCAT. Because how do you think they actually get those answer choices? Focus group study. Bunch of students making plenty of mistakes, and they put the four most common ones there. If you're finished, thanks for waiting patiently while others are working. We're going to make sure that everyone is on the same page. We don't have to rush today. It's not a double lecture day. Working, combining multiple topics together. We're just only working on stoichiometry, solutions, and solubility. Okay. Melody says it's 45 grams of H2O. Brooke says the same. Got an answer choice of 24 grams of H2O. Sorry, that was anonymous. We'll try to keep it realistic numbers. I think you're violating some laws of conservation of math or mass. 6.2 grams of water. Okay, sounds good. I know, right? Off the top of my head, I was trying to be punny already. Law of conservation of mass, not law of conservation of math. Okay, so let's take a look at this. So when we do these types of problems, yes, when we do these types of problems, first thing we need to do is need to balance, actually write and balance a chemical reaction. If necessary, a chemical reaction. So when I think of writing and balancing a chemical reaction, I think of it as the blueprints for how this chemical reaction is going to play out. How many parts of one thing do I need, right? So if we're just looking at the basics, very good for the person that just gave me that chemical reaction. So we're going to look at the basics. We have hydrogen gas plus oxygen gas is going to make water. So right now we have two hydrogens on the left side, two oxygens on the left side, two hydrogens on the right side, one oxygen on the right side. That's no good, right? So we need to balance it out. So now we have two oxygens, four hydrogens, four hydrogens. So good job for the person that totally messaged me. Yep, we got to make sure we remember to balance it, right? Because then you're just working with the wrong blueprints, right, Jonathan? So I think of writing my balanced chemical reaction. Yeah, totally. It's like, yeah, I only need one of those things. Wait, I needed two. I need two wheels on a bike? Oh, yeah, something like that. So write and balance chemical reaction if necessary. So in this case, it was necessary because it was unbalanced. Sometimes it's just naturally balanced. The second thing that I like to do is I like to calculate the molecular weight of the chemical species. So hydrogen H2 we know is like 2 grams per mole. The other one is oxygen. See you, Todd. Have a good day. Thanks for checking in. Thanks for always making us laugh. Oxygen is 32 grams per mole. And water is 18 grams per mole. Right? So hydrogen is 1 plus 1 is 2, right? Oxygen is 16 each. We love Todd. What you guys don't know, Todd also wrote all your chem books, chemistry and your organic chemistry books. So he's the main author. And all those questions, right? You can see his humor in all those questions. Yes, Todd is everywhere. Third step. You have to ask him that question, Noah. I think he's a little too old for that, but he might. I mean, if he gets bored, like from just teaching and being partially retired and whatnot, he might. Oh yeah, those USMLE books. I guess you've been doing them, Vinay. They are dry. They are so dry. They're written by doctors who have no sense of humor. So the next step we need to do is find the limiting reagent. So when we're given two objects that are reactants and they have a finite amount, I have. You got to remember, I almost was a doctor. I was this close, and like I was reading ahead. So this close. Got into med school, should have went, decided not to go. Companies gave me too much money to work. So, all right. So now we have to start with what we're given. To find the limiting reagent, we have to look at from the grams of hydrogen and from the grams of oxygen, how many moles of the product can we make? Okay. So we have 5 grams of hydrogen. There's 2 grams of hydrogen for every 1 mole of hydrogen gas. And then using our chemical reaction, for every 2 moles of hydrogen gas, this is our stoichiometric coefficients from our chemical reaction, we make 2 moles of water. Okay. So what you end up noticing, the grams of hydrogen cancel out, moles of hydrogen gas cancel out. We're only left with moles of water. The 2's cancel out. So 5 divided by 2 is 2.5 moles of water that we make. Okay. The other one is the one for oxygen. Do the same goalposting or calculations, right? So it's 32 grams of oxygen for every 1 mole of oxygen. And for every 1 mole of oxygen gas, we're going to make 2 moles of water. Right, so everything cancels out except moles of water again. And you notice that there's 64 grams. 64 divided by 32 is 2. 2 times 2 is 4 moles of water. So which one is our limiting reagent? Hydrogen or oxygen? Very good. Hydrogen is your limiting reagent, right? Because it produces the least amount of H2O available if we used all of it up. And last but not least, we need to solve for what we're looking for. In this case, we want grams, right? So since we're going to have 2.5 moles of water, and there's 18 grams of water for every 1 mole of water. So this is how we're using those stoichiometric ratios and your atomic mass to figure those things out. So 2 times 18 is 36. Half of 18 is 9. 36 plus 9 is 45 grams of water. So huzzah, I believe, to Brooke, and someone else also said 45. It was a while ago. Melody, you were the first one to say it. So good job for those who got it. If not, make sure you write all the steps and do all the steps. Write and balance a chemical reaction. Calculate the molecular weight of the chemical species. Find the limiting reagent between the two, and then solve for what they're asking you to solve for. Any questions on that?
Quick question. So would we have to know in this case, like, would we have to know the 2 grams and the 32 grams?
You can look that up. It's the periodic table of the elements has that,
Okay.
right?
And we'd be provided that information?
Yes, the one thing
Okay,
that
cool.
they've done in MCAT is the periodic table of the elements for both biological section sciences and physical sciences. Yep. That's the one thing. Hence why I spent all of last week going over. Sure. Why I spent all of last week going over the chemical, the periodic table of the elements. Yes, no calculators. You have to do it in your head. So know the atomic masses relatively, and then you can add them. Limiting reagent. Perfect. So let's go over it real quick. Hydrogen is 1 gram per hydrogen, and there's 2 atoms, so then it's 2. Noah. So each hydrogen atom is 1, so 1 plus 1 is the 2 grams per mole. And oxygen is 16, so that's why there's 2 oxygens, so it's 32. Okay, so let's take a look. Alep asked if we can go over the limiting reagent again. So if we take what we have, so with limiting reagents, yes, Jonathan's right. Calculator, no calculator, periodic table, yes. I'm assuming ALAP is if we take all of the grams of hydrogen and go all the way to completion, and take all the grams of oxygen and go all the way to completion, which one would make the least, right? And that one's the one that's going to end up getting used up first. Does that make sense, Alap? So since the 5 grams of hydrogen gas makes the least moles of water, that's going to be the one that ends up getting used up first. So hence, that's why it's the limiting reagent. Does that make sense? How I got it? The getting it part is just the stoichiometric coefficients. You can, but it's always good to do the conversion first into moles for everything, but they always give it to you in mass. So you have to do conversions to moles first, because sometimes you might have something that's you're using very little of it, but then you already also start with very little of it. So that's why I try not to do that at DTF and just look at the mole ratios only by itself. I like building a bike. I'm an engineer, Jonathan. I guess I am a fat guy. So first, so yeah, I'm surprised I didn't use the sandwiches example either. Sorry, go ahead.
Sorry, yeah, just another quick question. So step 3, like the last, column in those couple tables, you have 2/2 and then 2/1.
Yes.
Can you explain how we're getting those different ratios?
Yeah. So 2/2 is here. So that's why
yeah.
the balanced chemical reaction is necessary, right? This is why it's necessary, because you're getting that 2/2 ratio from there, and then you're getting the 2/1.
Oh, got it.
Here.
Okay.
Does that make sense?
Thanks. Yeah.
Yeah. That's why it's necessary to balance it, right? Because then, it's like Jonathan said, how do you build a sandwich, right? Or I like riding a bike, right? You need 2 wheels and a frame, right? Same thing. But he's using 2 slices of bread and a slice of cheese, right? So, but you can use that analogy. But if you don't have the correct stoichiometric coefficients, then you're not doing the correct chemical reaction. So we need to balance out the number of atoms that we have, right? So that's why. Good question. All right. Moving along. So now that we know that, and we can do these basic type of questions, let's give you one that I got personally for my MCAT. And these still come up every now and then for your FAQs, your independent questions that you have on your MCAT. So I want to know how many grams of calcium are needed to fully react with 1 gram of O2 to make calcium oxide. (1.25 grams, 2.50 grams, 3.0 grams, or 3.5 grams? We'll leave it at calcium 2+ to make it easier. But if you think about it, this is definitely what we call a redox reaction, Monica. And calcium is losing those 2 electrons to oxygen, right? Hence how oxygen becomes a -2, because initially oxygen has 0 oxidation state, right, in O2. Yeah, sorry. The analogy for the engineer in me came out, Jonathan. Not the fat kid in me came out. So Aditya is saying the same thing. So is Amanda. Okay, so let's take a look. Seems like majority of people have answered. So we have calcium, probably solid, plus oxygen gas. Oh, I guess this question's coming up a lot in private message. I was a bioengineering undergrad and a chemical engineering graduate student. This is definitely a one-way reaction. And we're going to have calcium oxide, right? Calcium's natural oxidation state is +2. Oxygen's oxidation state here is -2. They originally start with 0 and 0. We'll get into those oxidation states when we talk about redox within the next 2 weeks or so. Okay. I hear you. Sometimes if you don't practice it, it's easy to forget. So let's balance it right now. We have 2 oxygens on the left, 1 on the right. So we got to make sure we have 2 of these, and then that means we're going to need 2 of these. Sure. Where do they come from for the oxidation states? We'll get to that on when we talk about redox, Leandro. It's +2. Yeah, it's up from oxidation states. Yeah. So calcium becomes +2, which means what? It gave off 2 electrons. And look, looky, who picked up the 2 electrons? Oxygen, right? And if you think about it, what happens when we talked about last week? Calcium losing 2 electrons allowed it to go to noble gas configuration for its electron radial shell, right? Or orbital shell. And same thing with oxygen. By picking up 2 electrons, it too is perfectly happy because it's now at noble gas configuration for its orbital shell. Yeah, but it'll be good for the psych and social section. Wow, we are coming up with the puns today. This is awesome. Noble loser. And a noble gainer too. Oh man, sounds like you guys have been hanging around Todd a lot. Those are Todd's puns. He would probably try to copyright it. Noble loser. That's an awesome one. I like it. Okay, so now that we have our chemical reaction correctly balanced and everything, and we're assuming that we're exposed to air, so excess of water, oxygen. So I mean excess of calcium because it's a solid. So we have 1 gram of oxygen gas. There are 32 grams of O2 for every 1 mole of O2. And we're trying to find grams of calcium that are needed. So we need, for every 1 mole of O2, this is our stoichiometric coefficients, we need 2 moles of calcium, right? And then for every 1 mole of calcium, we can look this up from our periodic table of the elements. It's going to be around 40 grams of calcium. Okay, so everything cancels out. So you're going to end up with 80 over 32, and that simplifies down to about 2.5. So 80 over 32 grams of calcium, divide by 4. That's going to be 20 over 8, divide by 4 again. That's going to be 2 over 5. So 2/5 or 2.5 grams of calcium. Very good for those who are killing it today. All right. The next thing that we're going to lead to with this is the difference between a molecular formula versus an empirical formula. No problem. Here you go. Let me know when you're done, Michaela and Melody. Michaela, we're good? Awesome. So, molecular formula versus empirical formula. Because we're going to use the stoichiometry to figure out what the empirical formula and then postulate what are some possible molecular formulas, right? This is what you did in Chem Lab before. So the molecular formula has the actual mole ratios, and while the empirical formula has the smallest whole number ratio of atoms. So let's look, for example, ethene. We know that ethene is a 2-carbon, 4-hydrogen atom. So that's its molecular formula. The empirical formula is the smallest whole number ratio between the two of 4 and 2. And that's going to be CH2. Okay? So that's the difference between a molecular formula versus empirical formula. All right, so now let's take a look at how we can figure that out by using an application, right? So we understand the difference now, so let's look at an application of our stoichiometry to figure out our molecular versus empirical, and we're going to do what we call a combustion reaction. So we know combustion reaction analysis. So originally, this combustion reaction analysis was used back in the early 1900s to figure out what whale oil was made out of. So this was done back in the early 1900s by Michael Faraday. He would take some hydrocarbons. So what ends up happening? Yeah, that says whale oil. It's actually whale fat, right? Because that was the energy of the day. Way back when, right? Because you had to think about it. Chemistry doesn't start with us just digging up fossil fuels out of the ground, right? You think of hydrocarbons nowadays, right? You think of your methane, your propane, your butane, your octane. That's all like fossil fuels coming out of the ground. We decided to use, we use whale fat. That's why like the humpback whale, was going extinct. We would use it to heat all the lamps and stuff and get all the lighting, right? Before electricity was plentiful and readily available to the masses. So what you end up doing is putting your hydrocarbon in some chamber, and you're going to have oxygen gas, probably through some intake. It was. Think about it. We've been exploiting Mother Nature since forever. So you usually have some type of spark plug or something done with some electricity to get it to light up that hydrocarbon plus oxygen. Sorry, there should be a gap here. We're then going to go into a chamber. At the bottom of that chamber, we're going to have some magnesium sulfate. The whole point of having magnesium sulfate is so it absorbs water. And then there's another chamber that this goes to. At the bottom of that chamber, it has sodium hydroxide. And this absorbs carbon dioxide. Okay? So, knowing that, so a typical combustion reaction is some type of hydrocarbon, CnH2n plus O2 becoming carbon dioxide plus water, right? And you think about it, this is your typical car engine, right? Even the hybrid engine still uses fossil fuels like gasoline, which is an octane, which is a hydrocarbon. And you're combining it with oxygen gas, and we're giving off carbon dioxide, which we call the greenhouse gas now, right? And water. So both carbon dioxide are products of this combustion type reaction. So then my question then to you guys is how they'll present this as data. So we'll look at the magnesium sulfate and the sodium hydroxide, the mixtures in those jars. We'll look at them initially. So this is before the chemical reaction or chemical combustion. They're around 40 grams and 40 grams respectively. Then after the chemical reaction, this is around 49 grams and this is around 84 grams. We're assuming that those grams increases solely from water and carbon dioxide respectively. I want you to find the carbon to hydrogen ratio, and I want you to postulate possible hydrocarbons. If you can come up with 3, great. If you can come up with 4, even better. But, just any number of hydrocarbons you can think of that has that empirical formula. So here's your typical table and application. So we're trying to find the empirical formula, and from the empirical formula, try to postulate what the molecular formula is. And while you were doing this in lab, you would have sent this into mass spec, right? And the mass spec would have told you the molecular weight of your chemical at the end, and you would have been able to guess it based on your molecular weights of all the postulated hydrocarbons that you guessed. Yeah, it's still really sad because you think about it, whale has the most blubber, hence that's why they use whale oil the most. So Faraday was trying to maximize and figure out how many carbons and hydrogens that they had. Yes, 49 and 84, correct. We're trying to find the amount of water and carbon dioxide that was absorbed from our combustion reaction. So initial is before the reaction, final is after the reaction. Oh yeah, I'll go back to the previous slide so you can see it, Zoe. Magnesium sulfate absorbs water, and sodium hydroxide absorbs carbon dioxide. Yeah, that part was quick and it's a little small, so I didn't expect everyone to pick that up. but it's right here. So your sodium hydroxide absorbs carbon dioxide and magnesium sulfate absorbs H2O. There you go. So you're thinking it's 9 grams of water and roughly 44 grams of sodium hydroxide. Find me the carbon to hydrogen ratio. Correct. Okay. I think that's enough time. So let's take a look. We're going to figure out how many grams from the 9 grams of oxygen, how many moles of hydrogen we got. Okay. This goes back to the previous example and application, Amanda. So we're burning some hydrocarbons. The magnesium sulfate layer absorbed the water. That was the reproducts of that reaction, and the sodium hydroxide absorbed the carbon dioxide of that combustion reaction. Okay. So then the rest is just stoichiometry. We have 9 grams of water, 49 minus 40, and 84 minus 40 is 44 grams of carbon dioxide. That's how we ended up getting what we got. Does that make sense? Good. So from that, correct, final minus initial. So we need to know that water is 18 grams for every 1 mole of water. And for every 1 mole of water, we're going to have 2 moles of hydrogen, right? Because there's 2 H's in H2O. So we end up canceling everything out, and we get 18 divided by 18. So we get 1 mole of hydrogen that we produce from those 9 grams of water. We do the same thing for carbon dioxide. 44 grams of CO2 for every 1 mole of CO2. You're going to have 44 grams of CO2. Because oxygen 16, there's 2 of them, that's 32. 32 plus 12, which is the atomic mass of carbon, is 44. That's Aditya, that's what's going to lead us to the yes. Yes, stop typing in caps. Sorry for those who are typing to me in caps. It sounds like you guys are yelling. I was like, that's what caps means to me. I'm like, in a soft audible voice, please. So what's the significance of the moles of hydrogen? Because that's how we're going to determine. You're going to have 1 mole of hydrogen, and then we're going to figure out how many moles of carbon we end up getting. And that's how you determine the empirical formula. So for every 1 mole of carbon dioxide, it produces 1 mole of carbon. So 44 divided 44, it's also 1 mole of carbon. So the carbon to hydrogen ratio is CH, or 1 to 1. That's why we need to find the moles of hydrogen and the moles of carbon from what we started with, right? So that just means that, hey, the ratios, I had a question come in. How do I know that 1 mole of H2O makes 2 moles of hydrogen? There's 2 H's in H2O. Yeah. So that's why. And then there's only 1 carbon in CO2. So that's why.
Where did you get the 18 grams of water?
Adding that up from your periodic table of the elements.
Got it. Yeah.
16 plus 2 hydrogens, which is 18. 1 each. I had a question. Sorry, you might have said this already, but is the initial and the final numbers given, or did we grab those off the previous information? No, they're given off of a table. So if the application type of thing would be, here's the passage, it explains how combustion reaction works, and there'd be a table within the passage that gives it to you. So you're supposed to use and extract information from that table and apply it. So this is the type of the questions that the MCAT likes to ask nowadays. So that's why I'm presenting it to you this way. Does that make sense? So they know you guys know how to do, like, basic stoichiometry and stuff like that. Oh, so and another statement to come in. So then from there, so basically for the student that just messaged me, you stopped at this point and this point. You need to go 1 step further to figure out the number of hydrogens and the number of moles of carbon. Moles of hydrogen, moles of carbon. That was it. Right? If you ended up with half a mole of water, you stopped at this point. And if you ended up with 1 mole of carbon dioxide, you stopped here. Right? So you needed to go 1 step further and convert them into hydrogen and carbon to figure out the empirical formula. Does that make sense? Because in order to figure out what the C to H ratio is, typically most hydrocarbons are CN and CH2N, but not always the case. No, you can't do it just from simply that, because then you have to figure out, like I said, you have to go 1 step further to figure out the moles of hydrogen and the moles of carbon. Same student was asking me why we can't just use half a mole of water and 1 mole of carbon dioxide to figure it out. Yeah, you have to go 1 step further to figure out how many moles of hydrogen and moles of carbon are produced from those water and carbon dioxide molecules. Okay? Yeah, like I said, you stopped right here. You need to do one step further. Okay. So now that we know that, name some possible 1 carbon to hydrogen ratio. In this case, it didn't follow the C's, N, and H's 2N, right, for your hydrocarbon. This is a 1-to-1 ratio. Yay, benzene, right? It's a hydrocarbon, doubly bonded, allowing you to have 1 hydrogen at each one of these points. So 6, so this is what, C6H6. What else? So you also have ethyne. Right? This is your ethyne molecule. And you have your C double bonded C, single bonded, double bonded C, number of hydrogens. Anyone know the IUPAC nomenclature for these? So it's a bute, 1,3-ene, right? So it tells us where the ene groups are, or diene, if it's 2 enes. Could be triene, but just diene, sure. If you're using yeah, this is organic chemistry. This nomenclature, I know you guys are just like killing it today. You guys are killing it. You and your puns and your names. Everyone's more awake on Wednesday. No one likes Mondays, I swear. Okay, so that's your typical standard empirical molecular type formula application of it. Know how to use it. Pretty straightforward. Okay. Exactly. These jokes would like make any type of thing fun. Okay, so now let's take a look at solutions. And then we're going to look at solubility. Yeah, Noah, if you want, just, oh, I guess that is the plan. Everyone here is hoping to apply. Noah, if you guys know her or see her tomorrow, feel free, she can message me and I can send her the lecture notes, okay? So solutions and solute concentrations. So we need to know the difference between a solvent and a solute. Solvent is the fluid present in largest amounts. The solute is the thing that's being dissolved. So it dissolves in the solvent. The reason I say that solvent is the thing, the fluid that's present in largest amount. When I say fluid, it could be a liquid or a gas. It could be both. And you can have 2 liquids be in solution with each other that are mixed, where one isn't like completely dissolved in the other. Okay. So know the difference between the solvent and the solute. The solvent is the thing doing the dissolving, and the solute is the thing that's getting dissolved. Okay. The way we measure solutions is by measuring molarity. Molarity is moles of solute over liters of solution. The units are moles per liter, otherwise denoted as a capital M for short, for molarity. Okay. Keep in mind that molarity changes with the temperature. The other term that we need to know for solute concentration is molality. This is moles of solute over kilograms of solvents. So moles per kilogram, this is denoted as little m for units of concentration for molality. And this has no change with temperature change. So molarity changes with your temperature, mainly reason the liquid amount of your solution tends to like evaporate and go into vapor form, right? So that changes your overall concentration. With solutes and solutions, we need to know how to do dilutions. And what are dilutions first? Dilutions are simply adding solvent to decrease, sorry, there's nothing under molarity. Moles of solute divided by kilograms of solvent. Yeah. So adding solvent to decrease the concentration of solute. So simple dilutions are pretty easy. If you're adding 2 parts to a solution, you end up with a 3-fold dilution. 3 parts, that would have been 4, so on and so forth, right? The equation for simple dilution is simply molarity times initial volume is equal to new molarity times final volume, right? So if you think about it in units, it's moles per liter times liter, right? And that'll give you moles. So it's moles before is equal to moles after. So the amount of solute concentration that you have is still the same. You're just changing the amount of relative volume that you have in there to give you a different concentration that you have at the end. Okay. So this is the equation associated with simple dilutions. But you're typically doing the same thing, right? To find the concentration of the solution at the end, you take the moles of whatever your solvent is divided by the liters of solution. Okay. Let's give you guys a harder question dealing with that. So let's look at a harder dilution problem that isn't just simple dilution. And you can see this being used for any type of chemical mixture that we're going to have. So we have 50 milliliters of 0.1 molarity of sodium carbonate plus 75 milliliters of 0.4 molarity of sodium hydroxide. I want you to find the concentration of sodium ion after mixing. Yes, NaCO3. Can concentration and dilution be used interchangeably? Concentration just tells you how much moles per liter you have, and dilution is when you add solvent to that already concentrated sample. You got too excited, Brooke. You typed it in. Yes, it's nice when everyone's getting the same thing. Good. Awesome, awesome. Usually in a room with this many punny people that are funny and smart people, the majority is usually right. Graph question. Biomolecules has been moved. It's going to be with your SN1, SN2 lecture. That's when they're going to teach all that steroid and econosanoids together. Oh, that first question I gave you where the majority was not right. Yeah, that question is meant to do that. so don't feel so bad. One of those questions where it's like, yeah, everything's all wonky about it. Yeah, biomolecules has been moved to to the SN1, SN2 lecture, and they'll be teaching steroids then. I was told not to teach it today by Todd. So strictly just solutions. I mean, stoichiometry, solutions, and solubility. Okay. So everyone seemed to be getting the same thing, 0.32 molarity. So let's take a look. So you have 50 milliliters of 0.1 molar of Na2CO3. Apologize, that looks pretty gross now that I look at it again. And so 0.05 liters times 0.1 moles per liter. And then we're going to multiply by 2 because there's 2 sodium, right, moles that we have in there. So if you think about it, it's 2 times 5 is 10. Move the decimal place over, that's 0.1. So 0.1 times 0.1, this is 0.01 moles of Na plus. The other one is 0.075 liters times 0.4 moles per liter. So 4 times 75 is 300. We're going to move the decimal place 4 places. So this is going to be 0.03. Sorry. 75 times 4 is 300. Move the decimal place 4 places over because there's 4 decimal places here. That's how I'm getting these numbers, by the way. And this is moles of Na plus. And the final volume is 50 plus 75 or 125 or 0.125 moles of sodium plus, 0.01 moles of sodium plus. Because when this is dissolved in solution, this becomes sodium ion, right? Oh, it's just a multiplication. I'm multiplying it by 2 based on the 2 that we have in sodium. So we have 0.04 moles divided by 0.125 liters. It's going to give you 0.32 molarity or moles per liter. So very good to all of you who got it right. That's excellent. Not going to have a problem with dilutions on the test. And you can see this happening again when we talk about acid-base chemistry, right? This could have been some acid, 50 milliliters of some concentration of acid plus 75 milliliters of some concentration of base. You can also see this again when we're mixing things for redox, right? For oxidation reduction. So being able to figure out the concentration you're going to have after something mixes, super important so that you can actually understand how much of something you have when the reaction starts. Okay. All right, so now let's talk about solubility. For solubility, we're talking about breaking up a lattice structure to allow particles to move freely in solution. So when we talk about solubility, first term we need to know is dissociation. And dissociation is breakdown of ionic bonds. The next is we need to know what does it mean to be saturated. So saturated means as much salt dissolved as possible at a given temperature. We also need to know what is supersaturated. This is more salt dissolved than allowed at a given temperature. So when I think of supersaturated versus saturated molecules, right? If you ever did any baking, when you're baking and you're making simple syrup, right? 1 cup of sugar, 1 cup of water, right? You're allowing that sugar to dissolve into the water. So if you just left it at room temp, that wouldn't dissolve, right? That sugar, that 1 cup of sugar wouldn't dissolve in water. So what ends up happening is yeah, so the intermolecular forces will still stay there, but you're going to get it to dissolve because what ends up happening is the water molecules will slowly break off each ionic bond and break it down over time. Right? Think of like a cube of salt when you first put it in, right? Or a cube of sugar when you first put it in the water. It takes a while for it to break down, right? Unless you give it what? Kinetic energy by stirring it or by heating it. So when we're supersaturating something, we're adding in an extra energy, right? This free energy that we have from either heating it or stirring it to give it kinetic energy for those liquid molecules. So as those liquid molecules are moving faster, they knock off the ionic bonds from each other and break up those IMFs or the intermolecular forces that ionic lattice structure has. Okay. So when you get something that's supersaturated, then you're allowing more salt dissolved at a given temperature than possible, right? And then you end up with what we call a supernatant or that gloopy structure that you have when you form simple syrup. You guys have baked, right? Before, or you have seen simple syrup. If not, you've had Starbucks coffee before, right? So with the Starbucks coffee, you get all those pumps, right? Those pumps are just super saturated sugars. Yep. Exactly. Simple syrup is awesome in most drinks, alcoholic or otherwise. Yeah. Yes, beverages. That's a nice way of saying it. But yes, all those like super simple syrup allows you to make something that's sweeter because why? We're adding more sugar per unit volume than there should be there, right? If we just took a cup of sugar water and dumped it in, okay? Because of that supersaturated nature. And saturation is easy. So basically, if you keep it at that same room temperature without heating it, if you keep on adding it salt by grain, salt by salt, it will end up getting to a point where when you put in another grain of salt or a gram of salt, it won't dissolve anymore, right? And that's when you get to what we call saturated. Supersaturated is when you decide to activate it and give it more energy. What ends up happening when you get solubility or things dissolving in other things, the reason that water is able to dissolve and make sodium chloride look like it disappears because all the water molecules begin to solvate or surround the free ions and generate intermolecular forces between that free positive charge sodium and all the free electrons that you have on your water molecule. I'm not drawing at all, but imagine this is a solvation bubble that we're going to get. And then for the chloride, the hydrogens will do the same, right? And so they end up surrounding each one of them. So that's why when things are dissolved in solution, it looks like it's a homogeneous mixture of just the original solution, right? That's slightly cloudier, right? And that's where that absorbance comes in from Beer's law and taking spectrophotometry and looking at the absorbance of light through those molecules. But this is where it comes from. It's forming those solvation bubbles and breaking it apart, okay? The next thing that we need to know is the difference between solubility product and molar solubility, and which one is more important, okay? So KSP is commonly referred to as the solubility product. And if you think of the solubility product, think of it as the KEQ for soluble equations, right? So this is the equilibrium constant for solubility. And the other term that we need to know is X. That's called molar solubility. So how do we determine it? Well, we have to take a look at how many molecules that we're going to break down into. So X here is just simply the number of moles that dissolve until saturation. So this molar solubility tells us how many moles that we have until we dissolve until saturation. So the key rule between using KSP and X is when comparing salts, sugar, anything that's soluble, salts is just a general term for it, use molar solubility, not solubility product, okay? So let's take a look at some of the 2-ion samples, 3-ion samples, and 4-ion samples that you're going to get. So this is your MX. So you have some metal with some halide, right? And it's generally a solid ionic lattice structure. So these are all ionic bonds. With water, that's a liquid. It's going to go back and forth. You're going to get some metal cation that's aqueous and some halide that's aqueous. Majority of the substances that you use, KSP is always going to be greater than 1, so you know it's going to dissolve. And so I don't know how much it tells you about the side at which the reaction is favored. Halide. X is your halide. So think of your halogens, fluoride, chloride, bromine, iodide. Yeah. It's just to tell you the equilibrium constant, whether it's going to produce it or not. If it's less than 1, obviously there's not going to be soluble. So in terms of solubility product, this is going to be your concentration of your metal halide, a metal ion, and your halide ion, right? And you're going to get 1 of each, so 1 mole of each, so X times X. So you're going to have that be equal to X squared molar solubility. So when we're solving for x, this is going to be the square root of your KSP. These are for your two ion species. Example of this would have been sodium chloride, right? The next one is your 3, right? MX2 solid plus water. So this is your metal dication species, and you're going to get 2 of your halide ions. Okay, so in terms of KSP, you're going to get concentration of this 2 times the concentration of this, right? In terms of equilibrium, you're going to get x and 2x quantity squared, right? Remember, the stoichiometric coefficients are your exponents. Okay, so this is going to become 4x cubed, is in terms of molar solubility, is equal to KSP. So molar solubility is the cube root of your KSP divided by 4. Example of this would have been your magnesium chloride. And last but not least, MX3 solid plus H2O liquid is going to become M3 plus 3x halide ions, right? Example of this would have been your aluminum chloride. So your KSP, concentration of your trication times 3 of your halide ions. So that would have been what? X times 3x quantity cubed. These stoichiometric coefficients become your exponents. So this would have been 27x to the 4th. So the molar solubility for a 4-ion species would have been the 4th root of your KSP divided by 27. So we're always going to look at your molar solubility over your KSP, because for the most part, KSP is just telling you whether the reaction is going to dissolve or not, right? And generally, most of the KSPs that they give you for your MCAT, it's going to dissolve, right? Otherwise, why would it be in a solubility section? Okay. So let's look at how to do molar solubility or calculate it. So with molar solubility, the first way to make it you're right, they should have been included. I should have included it right here and right here. Thank you, Melody. So, sorry, my bad. When looking at molar solubility, first thing we need to do, and what we would normally do to figure out the molar solubility of a substance, we need to make a saturation. And measure absorbance. And to do that, we need to know what Beer's law is. So Beer's law states that the absorbance of a substance is equal to its extinction coefficient times the concentration of your sample times the length of the cuvette that you're using to measure. Okay, this is the equation for absorbance. This is using spectrophotometry. If you guys did chem lab in college, you basically mix something together and then you all rush to the spectrophotometer where you put that little cuvette in and you waited for the machine to do something. And this was the waiting lab where you just waited and waited and waited because it took a while for the machine to do the analysis to print out what fields you're absorbing. Okay. The second one is we could add salt gram by gram. Until saturation. Then filter, precipitate, right? Because it would have formed some type of solid, dry, and weigh. Precipitate. Okay. And the last one that we can figure out this molar solubility is using an ion exchange. Exchange. So we change a cation for hydrogen. So it's usually some type of column chromatography where we're putting something in, then it elutes out. So we're putting our metals in, or our dissolved metals in. It's going to bind to some beads, so or whatnot, and what comes out is your hydrogen that's getting kicked off from those beads that was originally bound. And then what do? We measure the pH. Hydrogen plus. We're exchanging this metal cation for H plus. And so we're just measuring that pH of it afterwards. We have a practical example of this where we're using it inside our house. Most Californians do. Anywhere where you're getting water from aquifers, you generally have to have a soft water filter. Okay. So let's take a look at this application. Yep. We're trying to get out things like calcium. Perfect. Sure. Yep. For hydrogen or for sodium, if you have this in your house, you'll taste it like when you're like, showering and you accidentally drink some of the water or drink any of the tap water in your house, you find that it's a little salty or it tastes sweet, right? Because in your mind, salt and sweet are the same thing for your taste buds. So let's look at this, the application. Of ion exchange. Most people have this, especially if you're getting water from aquifers, which most people do. We call this a hard water filter. I bring this up because there was actually a whole MCAT passage less than a year ago dealing with Boiler scale, which is calcium oxide buildup, relating back to that question I asked you on your pipes in your house. So hard water filter. So what are we doing? So most of the time, the water that we get from the ground has a lot of metals that are dissolved into it. And one of the undesirable metals that we have coming in is calcium, right? So calcium ion that's dissolved in water after that water has been seeped through the ground, absorbing all the metals and the salts and dissolving it and getting it down into the aquifers. And then when we pump it up, this calcium is already naturally existent inside. So when calcium water goes into our house or into our pipes at our home, when it dries up, because water, when you turn off the valves, In the water, it's going to start reacting with oxygen and forming calcium oxide. That's that white buildup that you have on your pipes after years and years of using water. And that makes your water flow really low, right, or weak. And so what it does is it's like atherosclerosis for pipes. It's basically narrowing the cross section of every pipe, making it so that there's less volume of water going across at any given point. So what we end up doing is we put this hard water filter through. There's a physical filter and there's a bunch of rock salt. So this is just your rock salt in there. And what ends up happening is that calcium will bind. So this is sodium chloride. And what ends up binding is our calcium ion plus NaCl becomes calcium chloride, which is a solute, which is a solid, right? It's what we call a precipitate. And we're going to collect it with that filter, and we're going to get sodium ions coming back out. So soft water, this is considered soft water because sodium doesn't react with oxygen, and this is considered hard water because calcium does react with oxygen to form that white residue buildup on your pipes and your shower heads. So anywhere where you have water that's being pulled from aquifers and at the rate at which most people are using it, if we don't have a readily lake available by you, like you do in the Pacific North, in the Northeast and in the Mideast, you will always be using that. Typically, yes, hard water is usually calcium oxide that's being produced after it dries up in their pipes. So it'll generally be calcium, it'll generally be chloride, and it'll generally be sodium. Because salt is so readily available, you can get it from anywhere by just drying ocean water, right? It's the cheapest way to make it. I'm sure you have like another, like some calcium something chloride derivative that they might use if you're not near the ocean and you can't get salts readily available. They might use something else with chloride in it though, Vinay. So don't quote me that this is exactly what they're going to be using, but yeah, majority of the time they're going to be using this because it's the cheapest. But yeah, if you're landlocked and you have no access to water or any major delivery, you're not going to pay a lot of money for salt. You can probably have some other calcium derivative of chloride, right? That's cheaper. But yeah, this is what we call soft water or a hard water filter, right? It's getting rid of all that calcium that you have in the solution in the water, right? And it's applying it to extract it out of your system. The last thing that we need to go over is what we call the common ion effect. Oh, ion exchange. So by measuring the pH, you can figure out how many concentration of because it's the negative log of the H plus concentration, right? And the negative H plus concentration is equivalent to your metal ion, right? And so you can figure out your molar solubility from there, because this is basically one of your X's, right? In your solution. Mm-hmm. Okay, last thing we need to know is common ion effect. So this basically states that the solubility of salt determined because one of the ions is already present in solution. Okay. So what is this simply saying? If you think about it, common ion effect is Le Chatelier's principle. So let's say we have some silver chloride, solid, tablet form. And some water. And you're going to end up with silver ion, aqueous, plus chloride ion, aqueous. So let's write that properly. Cl minus aqueous. So if I decide to drop silver chloride, by the way, this is something that I actually did. Okay. Way long ago. I think statute of limitations has already passed for it, but there was some stuff that we had in a lab. I'm not going to tell you where I worked, but we had in a lab, and there's a lot of silver chloride tablets left over, and I was like, let's do some chemistry. We can dissolve that, and then we can heat it up, and I'll get silver out of this. And silver was worth, decent amount back then. I had ended up getting a little chunk of silver that was like maybe a little bit like the tip of my pinky. So yeah, they were just gonna throw it out. So I was like, why waste it, right? I'm that's the Asian in me. I can't waste things. So I was like, let's do some chemistry. So I took some silver chloride, I dissolved it in water, getting silver and the chlorate after, and the chlorine after. I filtered out and got something to bind with the silver, and then heated it up. It filtered it, extracted it, and then ended up getting the silver, and then separated it again. So this is where solubility comes into play. Yeah, it's free money, right? I was like, intern, right, making next to nothing at like a huge lab, and they were just going to throw free money out, right? And I'm like, why would I waste free money? Right? I'm definitely not making enough money to be thrown because they were like, yeah, you can just throw that away. And I'm like, wait, there's like at least 1,000 tablets in here. Isn't this like straight silver? Like a majority of this is like silver. A huge majority of it was silver. But yeah, I just thought of this as my bonus. But if this water had sodium chloride in it, which is entirely possible because most water nowadays has some type of salt that's leached through the ground or through pipes that have cracked or through the grounds in the pipes in the ground, or even in your soft water filter that's coming out of the pipe. Since I was working in California at the time, if this chloride ion is already present in solution, it drives the reaction back this way, making that silver chloride less soluble, which means I couldn't get it from this silver chloride tablet into dissolved silver, which is what I wanted in the first place. Okay. So I ended up having to get distilled water. So by the way, distilled water is simply water without any free floating ions in it. So if I use distilled water with the silver chloride, I end up getting pure silver out of it. So it was kind of nice, but this is where the use of chemistry became applicable to the real world, where we're just not doing theoretical things anymore and looking at it. But if you think about it, Le Chatelier's common ion effect is simply Le Chatelier's principle. It says that if there's an ion already present in solution, you can't get it to dissolve as well, or it's not as soluble. Does not change molar solubility. No, it does not. But it does, and it does not change your KSP. in your system is all. But it just makes it less soluble. So you'll have less overall moles of it dissolve because of the extra ion of the thing I didn't want, right? I mean, you can't really like go like, I want chloride. They can't even sell that, right? You think of like those chlorine bottles they sell you, they're like $1 or $2 for like a giant like gallons worth of it. Correct. So solubility is how much more we can dissolve. Molar solubility is the maximum moles that we can dissolve in that solution. Right now, see, if I had known, Jonathan, I could have saved it for like 15 years. I could have been banking on both ends from those free tablets, silver and chloride. No, it's still pretty cheap. Like you can get like a 5-gallon bucket for like 100 something for like chlorine tablets. So, and that's the expensive ones, right? Yeah, but you think about it, like a gram of silver was worth like 100. So that's in retrospect, what's worth more money, and it's much easier to hide a gram of silver than a 5-gallon bucket of chlorine. Right? Back then, it was like $32 for a 5-gallon bucket of chlorine. Hell's no, I'm not carrying that out of the lab. But yes. Okay, so let's take a look at some questions to get you guys thinking about this. Oh, it's assumed that it's like you're adding it to this side because it's a free ion. So you're adding it to this side of the solubility for silver chloride, even though it's in water. And you think water of it being dissolved in solution and stuff like that. That's why.
Wait, sorry, which side? I couldn't see your cursor when you said that.
Oh, no. Since it's right here, it's on the right-hand side of the reaction. It's going to be driving it back to the left-hand side, so that it makes it less soluble. If that chloride ion's already in solution. Solution being water.
Okay.
Yeah.
Okay, thanks.
Yeah, because college kid in me didn't think about it, and I was using tap water, and I was like, and I was doing the math afterwards when I weighed my silver. I'm like, I'm not getting as much silver product as theoretically predicted, like way less. Like I was getting like 30% out of like what I thought would be. I was expecting something like 60% or 70%. I mean, there's some chemical error and stuff like that, but I'm like, whoa, this is way less. Yes, nerdy moments like this, where I'm like, hey, chemistry, it's coming into play. I'm making money. But yeah, then I just disposed of the chlorine gas and like it through a fume hood and stuff like that. Collected it, dissolved through fume hood, should be okay. It's the same if you increase, correct, though that is much harder to come by, Lexi. How much dissolved silver do you have lying around? Yes, it's always nice to have these like quick little nerdy moments. Exactly. I wish I had some silver lying around now, like silver chloride tablets, right? Jonathan and I would be making bank. He'll sell the chlorine. I'll keep the silver. It is. Okay, so let's look at some practice problems. Okay, everything's good. Everything's okay with the lecture part. I'm going to move on to doing some in-class practice questions. Okay. Actually, let me pull it up on my Notability real quick. We're on solution solubility. Okay. Actually, I need to write this out for you guys. It is not going to work. Too much stuff. So let's say we have, I want to know, so this is the third question of the day. What is the maximum number of grams of phosphine that's pH 3? Yes, that has a name. That can be produced from 1.5 moles of P2O5. Chemical reaction is P2O5 plus 8 hydrogen molecules creates 2 moles of phosphine and 5 moles of water. Answer choices are as follows: 51 grams, 68 grams, 102 grams, 25.5 grams. P2O5. Diphosphorus pentaoxide, right? Correct. Oh, Yannicka, wait till I get to acid-base chemistry. We'll talk about chemistry and relationships. We're going to have a lot of fun with that. That's how I remember my chemistry. It's all about bonding. Grams of phosphine. PHOS, PHINE. For some reason, on this section of my iPad, I think from my son smashing it too much, when I write find details numbers, oh, for A, 51. It comes out smudgy. So we're starting with 1.5 moles of diphosphorus pentaoxide. All right, got to remember all those prefixes for your molecules. If you don't remember nomenclature, go back, look at your organic chemistry book. It should be under there. $51, $68, $102, and 25.5 grams of phosphine is what we're looking for, pH 3. Got to get comfortable dealing with the math. So 1.5 times 2 is 3. 3 times 34 is 102 grams of phosphine. Okay. Any questions on that? I have a question dealing with the difference between KSP and which is more soluble after. Okay. Fourth question. Don't say anything, I'm going to move on. I want to know which is more soluble. Which is more soluble? We have calcium fluoride, CaF2, which has a KSP of 1.08 times 10 to the negative 10. And we have calcium carbonate, which has a KSP of 9 times 10 to the negative 10. That's all you're given. So we have to determine the solubility based on that. Not just given their KSPs. Well, everyone should have the number while they're working on it. Someone requested to go back. Okay, let's take a look. So, calcium fluoride breaks up into 3 ions, right? Calcium fluoride becomes calcium 2 plus ion plus 2 fluoride ions. Sorry, I'm just gonna always write, I'm so used to writing it in generic form. And calcium carbonate breaks into 2 ions. Remember, carbonate is one of those polyatomic ions that we need to know, right? 2 negative. So one's a 2 ion, one's a 3 ion. So this is equal to what? 4x cubed, and this is equal to x squared. So the molar solubility for calcium carbonate is simply the square root of 9 times 10 to the negative 10, which is 3 times 10 to the negative 5. Okay. The molar solubility for calcium fluoride is the cube root of 1.08 times 10 to the negative 10 all over 4. And so we need to do some mathematical manipulation so that this is actually doable, because right now I don't have a calculator. I'm not going to be able to do that in my head. But I can write this. I can rewrite this as the cube root of 108 divided by 4 times 10 to the negative 12. Right, I'm going to move the decimal place over 2 times, and it doubles my 10 to the negative 12, 10 by to 2. So then that becomes the cube root of what's 108 divided by 4? 27. Yep. And then this is the cube root of 10 to the negative 12. And remember that roots, so whenever we have something that's a root, it's simply x raised to the 1 over n. So this is 27th raised to the 1/3. This is 10 to the negative 12 raised to the 1/3. So that becomes 10 to the negative 4, and this becomes 3, right? Because this is 27 is 3 cubed. So it becomes 3 times 10 to the negative 4th. So which number is bigger? 10 to the negative 4 or 10 to the negative 5?
4.
Good. So we're going to choose calcium fluoride as being more soluble. Okay. This is how you use that KSP and your molar solubility together. So depending on your chemical species, so this is why when you have two chemical species that have the same number of ions, you can just simply look at their KSP, right? Because you're doing the same manipulations to them, whether it's square root, cube root, quartic root, right? Divide by 4, divide by 27, you're going to do the same thing. So then you can just look at their KSP. Lower KSP means, yes, more soluble. Well, less soluble, right? Look, this number is smaller than this number. Think about it. 10 to the negative 4 is what? 0.0001. 10 to the negative 5 is what? 0.00001. Which number is larger? No, it should be the same thing, right? Larger KSP means more higher molar solubility, which means it dissolves more things. Yes, Tiffany made that mistake earlier. I thought you looked at molar solubility to determine solubility, not KSP, given that KSP is smaller. Yes, that is true when you're comparing things with different number of ions. But when there's the same number of ions, you can just simply look at the KSP.
Can I ask a question?
Sure.
So for the KSPs that were given at the beginning of the problem, I said CAF2 because that's a lower number than the KSP given for CA,
No.
right?
We're comparing molar solubilities. This
Yeah.
is
But
a
I
large
mean,
number. 3 times 10 to the negative 4 is larger than 3 times 10 to the negative 5.
yes, but so I'm asking then, so you can't look at the KSPs here and compare them.
No, because there's different number of ions in the molecules. That's why we have to look at molar solubility.
Okay, thank you.
When they're the same, you can look at the KSPs and compare them. That's what I'm saying.
And when they are the same, then you want the lower KSP, right?
No, you want the higher KSP, the one that does more.
Okay.
Higher KSP is going to result in higher molar solubility, right? If you're doing the same calculations to it. Okay.
Question. KSP is the K of equilibrium for solubility, right? That's what it is?
Yeah, it's the equilibrium constant for solubility. And we're going to go over a bunch of equilibriums. I don't know why they don't have me teach equilibrium before any of this stuff. Like, I'm going to teach equilibrium when I teach kinetics to you guys, which kind of makes sense, but also should be something that's covered way earlier than later. But we're going to go over Ka, Kb, KSP. Those are all equilibrium constants. Cool?
Yep, thanks.
Yep, no problem. Ka, when you talk about it, it's just the acidity, solubility equilibrium. So the higher the Ka means you have more acid dissolved in solution. So very analogous to higher KSP means you have more molecules dissolved in solution. To answer your question, Michaela. Okay, I'll be around until 4:30. If anyone has questions, feel free to ask from lecture. Otherwise, I will see you guys next week. I will have office hours Thursday. I'm gonna set it from 2 to 4. Oh, actually, you guys have class on Thursdays 2 to 4, huh? I'll do. Are you guys free in the morning? Working. Okay, that's no good. Because I'm busy until like 7. Like after I get off with you guys, I actually have like work until like 7. I prefer not to do weekends just because that's family time. And you guys should be doing practice tests on those days anyway, because that's the only time where you get like a full chunk of time. So when you guys are using your Saturdays and Sundays, right now it's fine to study, but you should be using it to do your practice exams and stuff and get full lengths in if you guys want to start early. But that's what your Saturdays and Sundays should be used for, because I think that's the best time that you guys can have free time where you're not working to do it. I know you'll only have TBR classes until a certain date, Amanda, but after that you're going to be free. And then like the last 2 months that you have, you're basically studying on your own with like having some office hours and now here and now between me and Todd. Yeah, it's tough to find time, but right now I have time. I can do every other Wednesday, like this Wednesday, not next Wednesday, but the Wednesday after. I can do 4 to 5 office hours. Monday, sadly, I have class. I guess I can do office hours after from 4 to 5, but like, I mean, I'm already doing that anyway. So, I mean, I'll answer questions after classes on Mondays. And I believe Todd has office hours after my physics and my G-Chem lectures as well. Yeah, it's interesting. I'm just trying to find a time that works for you guys because I know you guys don't get off of work preferably or classes until like after 4. I like to do it before then, but I mean, it's tough. Tuesdays I can do 2 to 3. Actually Tuesdays 2 to 3. Does that work for everyone? You have class on Tuesdays? Oh. It seems like the rest of the class, Alexandra, doesn't work for them for Thursday mornings. I think everyone has work. Oh, okay. So 2 to 3 you have class. Oh, that wasn't listed there before. Yes, once I have it all down, Marissa, I'm gonna have it listed for Josh, and he'll put up all my office hours then. Okay, yeah. So I need to clear it with them once I get a chance to get in touch with Josh for setting up all the office hours. After the 8th week, generally you'll be done with the weekend lectures like after week 8. But I personally like weekends because that was the only time I have free time for myself to think and answer all like my huge questions and do long-term tests, right? Because your class is only for a certain period of time. So you'll have like either the morning free or the afternoon free. And I can do like a majority of my exam on that time. Yes, take care. Appreciate you guys. I will see you guys on Monday for sure. You too. Have a good evening. Bye, Tiffany. Bye, Lexi. Thanks, Jonathan. Thanks for all the puns. Man, you guys were killing it today. Like I was just like rolling. Oh man, it was good to work out the sides. Exactly. I don't know if you guys had a lot of Todd or something, but like If you hang around Todd, those are the types of jokes he has all the time. He's just nonstop punny.